Sampling distributions play a fundamental role in statistical inference. In this session, we will learn about the sampling distribution of the mean, but the concepts apply to sampling distributions for other statistics. By the end of this session, you will be able to distinguish between a parameter and a statistic, define sampling distribution, define the standard error of the mean, explain the central limit theorem, and describe the effect of sample size on the sampling distribution. A population represents the entire group of individuals being studied. It could be a large group, such as the population of all 6th grade students in the United States, or it could be a small group, such as the population of students with disabilities in Albemarle County. Either way, the population is the focus of your study, and your goal is to learn about a population parameter using only sample data. In most practical research, you do not have the financial resources or the time to collect data from every member of the population. As a result, we often work with a random sample from the population and use sample statistics to make an inference about population parameters. For example, we use the sample mean x bar to estimate the population mean mu and the sample standard deviation s to estimate the population standard deviation sigma. However, given the role of random selection, our sample estimates will be different from one sample to another. This situation gives rise to the question, how much do we expect the sample mean to change from one random sample to another? To get a better understanding of sampling variability, let's consider a short example. Suppose we would like to know the average IQ score among the 100 students who registered for tutoring at a local high school. This slide shows IQ scores for everyone in the population. The population mean is 99.2. In practice, you would not know the IQ scores for everyone in the population. They are shown here just for an example. IQ tests take about an hour to complete, which prevents you from testing everyone in the population. Therefore, you decide to draw a random sample of 10 students from the population and test them. IQ scores for the 10 participants in your study are highlighted in orange. The sample mean is 90.4, a value slightly below the population mean. What happens when we draw another random sample of 10 students? The sample mean is now 96.7. It is closer to the population mean, but not exactly the same. Chance is the only reason the new sample mean is different from the last one. Chance is also the reason our next random sample will also have a different value. This time the sample mean is slightly above the population mean. If we look at these three samples, we can get an idea about sampling variation. For 3 random samples, the means were 90.4, 96.7, and 101.8. More specifically, we can compute the standard deviation of these 3 values and obtain an estimate of the sampling variation. These values have a standard deviation of 5.7. If the standard deviation of the sampling distribution is large, we would expect the sample means to be notably different from one sample to another. On the other hand, if the standard deviation of the sampling distribution is small, we would expect the sample means to be very similar. The standard deviation of the sampling distribution has a special name. It is called the standard error, and it quantifies the variability in a sample statistic. That is, it tells us how precisely or imprecisely we estimated the population parameter. This brief example with IQ scores only used 3 random samples, but it illustrates the basic idea behind a sampling distribution. A sampling distribution is the distribution of a statistic over all possible samples of size n from the population. It provides all of the possible values of a test statistic and the probability of observing each possible value. Although we obtain a sampling distribution by conceptualizing a process of repeatedly drawing random samples, we don't actually have to repeat the process of drawing random samples. We can draw a single random sample to estimate the mean and compute the standard error of the mean by dividing the population standard deviation by the square root of the sample size. To reinforce the idea of repeatedly sampling from the population to create the sampling distribution of the mean, let's use another example. We will use the same process as the last example, but instead of drawing only 3 random samples, we'll use a computer to draw 200 random samples. The population distribution will be a uniform distribution on the range from 0 to 10. This distribution has a rectangular shape because every value in its range is equally likely to be observed. It has a mean of 5 and a standard deviation of 2.89. In the following animation, we will draw random samples of 30 values from a uniform distribution and compute the sample mean. We will repeat this process 200 times to obtain 200 values of the sample mean. This figure shows all of the parts that are involved in the animation. In the upper part of the figure, the red tick marks represent each of the sampled values. The mean of these values is marked with a solid blue dot. In the lower part of the figure, you see a histogram that illustrates the distribution of the sampled means. That is, the histogram is the sampling distribution of the mean. It looks unusual in this figure because we have only drawn one sample, and the histogram illustrates the distribution of this single mean. Once the animation begins, you will see the red tick marks change, another blue dot appear, and the histogram change shape. Let's take a closer look at the final image from the animation. You can see that the mean of the sampling distribution is 5, which is the same as the mean of the population distribution. If we apply the equation for the standard error of the mean, we get 0.53. As such, almost all of the sample means are between 4 and 6. Perhaps the more interesting feature of the sampling distribution is its shape. How does the shape of the sampling distribution compare to the population distribution? The population distribution was rectangular in shape, but you can clearly see that the sampling distribution is bell-shaped. It is unimodal, symmetric, and values near the mode are more likely than those distal from it. Indeed, the sampling distribution in this example closely approximates the normal distribution. This result is due to the central limit theorem. The central limit theorem states that as the sample size increases, the sampling distribution of the mean tends toward a normal distribution, even if the population distribution is non-normal. In addition, if our test statistic is a sum or a mean, the central limit theorem allows us to use a normal approximation of the sampling distribution, even when we do not know the population distribution. Let's look at a few more animations to see the effect of the central limit theorem on the sampling distribution. We will use a chi-square distribution with 3 degrees of freedom as the population distribution in all of the remaining animations. This distribution is highly skewed. In the first animation, we will draw a sample of one observation, compute the mean, and plot it. After 100 replications, what will be the shape of the sampling distribution? As you can see, the sampling distribution looks very much like the population distribution. It is positively skewed. It does not appear normally distributed, but that is expected. The sample size is too small for the sampling distribution to be normally distributed, according to the central limit theorem. Let's see what happens when we increase the sample size. In the next animation, we will use a sample of 8 observations. The sampling distribution still appears to be like the population distribution and not normally distributed. Let's increase the sample size again. This time we will use samples of 30 observations. The sampling distribution now appears to be much more symmetric and more closely resembles a normal distribution. According to the central limit theorem, the sampling distribution will become more normally distributed as the sample size increases. And once you have a sample of about 30 observations, the sampling distribution reasonably approximates a normal distribution. Let's look at one final animation. This time we will use a large sample of 125 observations. This sampling distribution is clearly bell-shaped. We can have a great deal of confidence that it closely approximates a normal distribution. Because of the central limit theorem, we can safely use the normal distribution as the sampling distribution of the mean when the sample involves 30 or more observations. This is helpful because we don't need to know anything about the population distribution. As long as the sample size is large, we can use the normal distribution as the sampling distribution of the mean. In watching the last few animations, you may have noticed another effect of the sample size on the sampling distribution. As shown in this figure, the standard error decreases as the sample size increases. To see this effect in action, we can plot the theoretical sampling distribution for sample sizes that range from 2 to 200. In the next animation, notice how the variability of the sampling distribution decreases as the sample size increases, and how the distribution becomes more concentrated around the mean as the sample size increases. Sampling distributions play a fundamental role in inferential statistics. They are based on the idea of repeatedly drawing samples from the population distribution. As the sample size increases, the sampling distribution becomes more concentrated around the mean, and it approaches the shape of a normal distribution. As a result, larger sample sizes provide more precise estimates of the population mean and allow us to use the normal distribution to approximate the sampling distribution.